Alrighty, so today we're going to prove something called the triangle inequality. And this inequality is probably one of the most famous in mathematics and is commonly used in analysis. And one of the reasons for that is it has a really nice geometric interpretation for the reals. So letting, just for a second, perhaps a, b, and c be real numbers, we have that the triangle inequality asserts that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And the reason for that is if you paint a and b perhaps as even vectors, it really doesn't even matter, and you let that be the vector a, and maybe that's the vector b, well then the sum is just simply going to be the resultant vector from those, right? So that's going to be the sum a plus b. And so all of those, of course, have magnitudes, and just based on facts about triangles, you know that this distance is always going to be less than the sum of these two distances. So that's kind of where the triangle inequality comes from, and it's quite a feat of amazement that this holds true naturally for complex numbers. Okay, and so in order to prove this, the first thing that we're going to need is a little fact, and so I'll just state this as a fact. And so we'll say for a and b real, we have that if a squared is less than b squared, that's going to imply that a is less than b. Okay, and so I'll have you kind of prove that as an exercise. And the other fact is, the converse is false. It is definitely not true. It is definitely not true. For example, if I have something like -6 being less than 4, that is a true statement. But if I square both sides, it is not true that -6 squared is less than 4 squared, right? Because 36 is not less than 16. So this is actually false, but we're going to kind of play around with this just a little bit, all right? So let's go ahead and get started. And in order to prove the triangle inequality, okay, so this is actually going to be pretty challenging without using complex conjugates. So if you know what those are, no you don't, because they're introduced in problem 2. And so what I'm essentially going to be doing right now is I'm just going to mess around with this. Okay, and the first thing that I'm going to do is realize that with moduli, remember moduli by definition involve those nasty square roots that I don't want. So in order to get rid of all of those, or at least most of them, I'm going to square both sides of this inequality. And if I can show eventually after squaring both sides of this inequality that I get something that's automatically true, then the reverse direction holds. Because remember, if a squared is less than or equal to b squared, that's going to imply a less than or equal to b. Okay, so that's kind of where my head's at, but we're just kind of messing around with this, all right? So let's recall that, I defined z1 to be x1 plus iy1, and I defined z2 to be x2 plus iy2, which means that the sum is going to be x1 plus x2, and the imaginary part is going to be y1 plus y2. All right, which means that the modulus of z1 plus z2 is going to involve a square root, and by squaring both sides, I actually get rid of the square root. So this is simply just going to be the real part squared plus the imaginary part squared. Okay, so that's essentially what I have. So on the left-hand side, and I am going to just kind of do it like this. So the left-hand side of this inequality is going to be that mess. So let's go ahead and just, FOIL everything out. So this is going to be, x1 squared plus 2x1 x2 plus x2 squared plus y1 squared plus 2y1 y2 plus y2 squared. So I just FOILed this out and I FOILed that out. Okay. Now the right-hand side of this inequality, well, when I FOIL this out, they're just real numbers, right? The modulus of Z1 and the modulus of Z2 are just real numbers, and so I get, just FOILing that out, modulus of Z1 squared plus 2 times the modulus of Z1 modulus of Z2 plus the modulus of Z2 squared. All right, and by definition, we can take what the modulus of Z1 and Z2 are. That's just going to be the real part squared plus the imaginary part squared. We don't need the square root because we're squaring the moduli. So this is simply going to be x1 squared plus y1 squared. All right, plus 2, and I'm going to go ahead and leave this alone for now, modulus of Z1 modulus of Z2 plus x2 squared plus y2 squared, the real part of Z2 squared plus the imaginary part of Z2 squared. Okay, so that's great because now we can compare and we see that that's the same as that, that's the same as that, that's the same as that, and that's the same as that. And so ultimately what we have is our inequality is now turned into 2x1 x2 plus 2y1 y2 less than or equal to 2 times the modulus of Z1 modulus of Z2. Okay, so if we can show that, then we're done, because then as a result, we can add a bunch of stuff to the left and right-hand side to get that less than or equal to that. And if that's true, those are just written as this. And if something squared is less than something squared, that's going to imply that that is less than or equal to that, which is what we wanted to show. So it's a little bit of a messy chain of logic, but hopefully you can follow it enough to see what we need to do next. So first of all, of course, I'm going to erase the 2's. I'm going to try to at least. So right, those are common to all of them. And so we now have to prove this. And so to prove this, I'm actually going to do the exact same thing again. I'm actually going to end up squaring both sides. Okay. Before I do that, though, I'm going to note that based on something that we actually just proved, this thing, specifically this thing, is really the same thing as the modulus of Z1 times Z2. Okay, so the product of moduli is just the modulus of the product. And so now I'm going to go ahead and square both sides. And just, again, I'm messing around, and I'm just trying to figure out what's happening here. Okay, and so I'm going to go ahead and do this. So this is going to be, x1 squared, x2 squared, plus 2 times the product of x1, x2, and y1, y2, plus y1 squared, y2 squared. And I already did this, right? I already expanded the product out, I think, in the previous video, so I'm just going to kind of do that. All right, so this is what I ended up getting. And now things are starting to become a little bit more interesting. Clearly, these terms cancel. These terms cancel as well. And it looks like I didn't really get anywhere. However, I'm going to go ahead and move this term over. This complicated 2x1, x2, y1, y2 term. And so now what I get is I get the following statement. I get 0 less than or equal to x1 squared, y2 squared minus 2 x1, x2, y1, y2 plus x2 squared, y1 squared. And believe it or not, that can actually be factored, right? Because I can write this in the form something squared. I can write this in the form something else squared. And this is simply going to be minus 2 times the first something times the second something. I just shuffled around the order of the terms, but no big deal. And so this is really going to be saying that x1, y2 minus x2, y1 squared is bigger than or equal to 0. Well, guess what? That's always true, because this is a real number, and any real number squared is just non-negative. This is what we would call in math a tautology. Since this is true, that's going to imply what? It's going to imply this is true, which implies that's true, which after you add this to both sides, then we're just kind of undoing everything that we did. And eventually, we're going to get back up to stuff that looks like this. But remember, as I said, this is essentially saying that a squared is less than or equal to b squared. And then you can go ahead and imply from that that a is less than b. So we did that a couple of times. But from this, we can work our way up and get that the triangle inequality is indeed true. So, bit of a messy way of going about it, but I actually like this way of going about it because this is kind of what math is sometimes. It's about messing around with inequalities and throwing everything you have at the time and ultimately getting something that's true. And so as an exercise, I encourage you to actually write a real proof of this, starting with maybe this fact right here and going from there, okay? But other than that, that is part D. All right, so part E says to show that if the modulus of z is non-zero, then the modulus of the quotient 1 over z is equal to 1 over the modulus of z. And so basically, if these were real numbers, this would be true just by kind of the definition of absolute value, or at least those properties. And so we want what's true of real numbers to be true of complex numbers. But it turns out that the real numbers are really just kind of a subset of the complex numbers. And so a lot of these properties do kind of hold true with a couple of important exceptions. And so let's just do this by the definition again. So we know that z is, some x plus iy. And so what's the modulus of the quotient? Well, first we have to figure out what 1 over z is going to equal. And so that's going to be 1 over x plus iy, and we need to write that in the form real number plus I times imaginary. And so to do that, you might remember from high school or something that we really multiply by the conjugate, although we're not defining it at this time. We're just noting that if we multiply by x minus iy divided by x minus iy, and again, it should be noted that if I take a complex number divided by itself, that still needs to equal 1. Otherwise, the field properties just kind of break down. But if I do that, then I get x minus iy divided by x squared plus y squared when you FOIL that out. And then I can essentially divide this into both of these terms. Okay, and so this is essentially going to equal x divided by x squared plus y squared, we'll say plus I times a negative y over x squared plus y squared. Okay, and so then we want to figure out the modulus of this guy. And so what's the modulus going to be? Well, the modulus of 1 over z is just going to be the real part squared. So that's the real part, and we're squaring it, plus the imaginary part squared, and then, of course, square root. Okay, and so the 1 over x squared plus y squared can essentially just come out. Really, of course, that's squared. And then in parentheses, we have an x squared plus y squared, right? Negative y squared, if it's in parentheses, is the same as a positive y squared, so we get that. Okay, and then I think we're almost done because this is going to equal. Technically, we do need absolute value bars around this, 1 over x squared plus y squared. And this was actually by a previous property Okay, times, let's see, the square root of x squared plus y squared. All right. However, we don't need those absolute value bars because this thing is definitely not 0 because we assumed that the modulus of z was non-zero, right? So since this wasn't 0, that implies surely z can't be 0, which means x and y both can't be equal to 0. We already kind of did that argument. Okay, so we're safe there, and this thing has to be positive. So we can safely drop these absolute value bars. And then we're just going to use some properties of real numbers, right? This is to the 1/2 power, and this is to the first power. And so really, that's just going to amount to this being 1 over the square root of x squared plus y squared, which by definition is the modulus of z. So we indeed proved what we wanted to prove.